So
We got it.
there you go.
Yeah, let's go ahead.
And let's go.
Mathur presentation for his master's project advance.
Yes,
Master's.
master's thesis. So hello everyone. So I'm going to present my master thesis, which is titled as DynaLay. It's an introspective approach for selecting the layers in any deep neural network. So first of all, I would like to thank my committee members, Dr. Sergey Place, who's my advisor, and committee member, Dr. Armin Hiraji. And I am really grateful for all the things that you have already given me and all the support that you have shared and for this idea to be built upon. So yeah, let's go ahead. So I've been studying the problem for machine learning for the last 2 years, and for those who know me, knows that I'm someone who's willing to jump on any amazing machine learning problem, and it's really great that how we are making amazing progress, and like of course, like as you can see at that as well, like how my curiosity lies because how much I post on our deep learning channel as well. So in any machine learning or deep learning network problem, we have seen that it has revolutionized a lot of sectors, be it computer vision, natural language processing, reinforcement learning, and right now the most trending part, which is the generative AI. But as we go ahead, we can see like the as we push the field of deep learning ahead, we'll see like a lot of complexities and the computational cost increases a lot. And that's where we question it, like why, despite all the advances in the deep learning, the most model, they lack introspection and they don't have the ability to adaptively select or computationally pathways or layers which are best suited for individual inputs. And that's what we wanted to find out and check, like if we can do something in that. And also the capability in this case is very vital because you can also optimize any resources or enhance the performance here. And that this work we saw, which it was surprisingly, it was not done by a lot of people as well. So my research, it aims on introducing a new architecture itself. It's called DynaLay. And we wanted to make sure that this is a self-introspective architecture that incorporates reinforcement-like agent for dynamic layer selection. When I say in reinforcement-like learning, we don't want to be associated with reinforcement learning at all, but we just want to take the parts of reinforcement learning, which is the agent thinking, and make it like a CPU for our layers. So this we will be discussing ahead as well, like how the agent actually works and how it does everything in person, everything in real time, and chooses the most appropriate layer to execute and optimize the whole network. So before we even go to the main architecture, there are few things that we have to understand so that we are familiar with all the aspects of each and every part that we try to implement here. So one of the most important and the crux of this is the implicit layer. We have to explain this because we'll be seeing the parts and the implementation for this in each and every aspect of our architecture. So what is this? So instead of specifying how you compute the layers output from any input, we specify the conditions that we want the layers output to satisfy. And that's what the implicit layer is. So just to give you a basic example. So let's say you have a network which has let's say you have a function which is f, and you have some input x which is the application of z. So where we have such that we have a function where z is equals to function of x. Then in this case, the implicit layer would be defined by the function of x comma, like in the function of g, that is x comma x into z in the real numbers dimension. And that is a joint function for both the x and the z for satisfying some constraint. For example, you have the root finding equations. So we want to, in this case, we want to find Z such that you have a function G where your inputs X and G is equals to 0. And that's a very simple, it's a simple way of telling how you can find any root of any function. And this is something that we have learned way before in high school or in masters as well. But why do we actually need fixed point iteration, right? We want to slowly adopt the we want to slowly adopt the part which we have already seen before of implicit layers, and we want to bring it to the deep learning part as a root of the particular equation. And to introduce this layer, suppose we have an input and output X and Z, which is again in the dimension of R, of the same dimension, and consider the following approach to computing the output of Z as a function of X. So here Z is basically Z, let's say if it's equals to 0, then you will have some condition that will repeat until your convergence, so that your Z, which is equals to the activation function of that, of the weights input and your bias, is going to be implemented. Now, what makes it very interesting is like, let's in this case, for any particular parameter, which is weight, or which is W in this case, it can be weights or anything, the equation is going to be, equation is going to find a point, which is X star, that will be in the equilibrium part of both the input as well as the function. And that is the solution for the root finding equation that we have been seeing before as well. So that is very interesting. But then why does it happen? So before this, there's a theorem which was introduced by Stefan Benosch. It's called the contraction mapping. So just to explain this in a very simple term first, so a contraction mapping, it's like a game where you keep moving closer to a specific target point each time you take a step, right? No matter where you start. As you keep taking the steps accordingly to, let's say, some certain rules, you'll eventually end up very close to the target point. In this way, a contraction mapping brings you closer and closer to a fixed point, or the target in this case, ensuring that you will eventually be getting there. And that's what, in simple terms, Benosch fixed point theorem says. So in this case, you have a metric space, which is M. It is called a complete space, in which every sequence M converges to M again in the same space. And so the theorem basically says you have, let's say you have some random variable X for some dimension, and you have a non-empty complete metric space, then the contraction mapping will eventually reach a unique fixed point X star, such that you have the function X star is function of some X star is equals to that X star, and that is the unique fixed point of that function. So this gives us a clear idea of what exactly fixed point theorem is. Why are we using this? We will be checking in the next few slides. But it gives since we will be using fixed point iteration in most of our, like that's the crux or the core of our algorithm. So it's better to introduce this before. Now, in order for us to check like what the work that we have done, we did some literature review. In this case, we have so the main part which was done by PJ Verbos in 1990 and Pineda. They established the fixed point iteration in deep learning and the recurrent neural networks, how you have the recurrency in any function. So they introduced that, and they did introduce it, but it was not as a foundational architecture component. Now the next part, which was very famous, that was by Alex Crave. That was done in 2002, I think. So they focus on the architectural adjustment, but not how it is done in real time or during inference. So again, there are a few other networks which was called PonderNet, which was again established in, I think, 2012. And they also had, so this was released by Google, where they had an adaptive computation, just like how you have in ACT, but they lack any layer-wise adaptation. and any complex operation that has been done by fixed point iteration. Now, there's another network which is called the deep equilibrium networks, which was done by which was done by PhD candidate Shiba Bai from CMU in 20. I guess it was done very recently, like 2 or 3 years back, where you.
2019. That's why you need to.
2019. Yeah. 2019. So they use a fixed point iteration with implicit differentiation, but they also used complex solvers, like, for example, Banosh solver, and which did take a lot of time for them to compute it efficiently. But one question that comes into our mind is, why exactly do we need a fixed point iteration here, right? So I wanted to introduce this game of life. In this case, it's Conway's game of life, where it's basically a cellular automation where each cell's future state is determined by its neighbors, right? So we can see in the initial grid. So we have the initial grid configuration, and the rule of this is basically, if you have in the neighbors of it, if you have more than 3 cells which are alive, then you will be dead. And if you have less than that, then you will be alive. So in this case, even though you can do these with certain rules, we can establish that even if you use just a single layer CNN and just a single filter as well, you can do the same thing that you have been doing with the rules. And a very astonishing thing in this case is that this is like a self-organizing system, right? So Game of Life organizes themselves based on some simple rules to create some complex patterns. Similarly, your CNN, or like the architecture that we are going to introduce, they are going to use simple filtering mechanism, or in our case, simple reward functions to make complex decisions, but about some layer selection. Also, they are very adaptive, because much like any in CNNs, you can choose, or you can see like which input needs to be processed, and which input needs to be processed properly based on the filters that you have. So this is a real world application that we wanted to show you, and why is it important. Now this example is being shown by using CNN, and you can see the total time that it takes just for running 25 iterations by rules is like 0.225, but using a simple CNN of 1 layer, it's taking 0.03. So imagine if we can stack multiple layers, or make it more dense, or make it more complex, then how efficient this will be. And this was the core novelty that we wanted to introduce in our problem statement. So our core novelty lies here. Core novelty lies in the model's introspective ability to recompute the results of more difficult inputs during the inference, and adaptively selecting the layers such that for each sample based on its unique activation profile. So what this will do is this will also optimize both your accuracy and your computational efficiency, as you will be seeing in the results section later. So any questions by either of the committee members till now?
Not from me. I mean, do you have any questions?
No, go ahead. Go ahead. Thank you.
All right. Thank you. So I wanted to introduce the contributions that we have done in our architecture. So first of all, we introduce a real-time introspection into a deep learning network, and we achieve the balance between any computational efficiency or model performance, right? And the key features of this, as we discussed before, are the fixed point iteration of layers, as well as the reinforcement learning agent that will adaptively select the layers which are there in the network. So we did this, but then it's not just we wanted to design this model as closely as something that can be used with any other foundational model as well. Like, for example, you have CNNs and LSTM. So we wanted to make this a more model agnostic architecture. So we did a lot of experiments in that as well, that we can see later in this results section. So let's move forward to the methodology of this. So our architecture, it uses two two networks. First is the main network that will be that can be anything. It can be like a full linear layer or CNN layers or LSTM layers, or and the other part of this is the agent network. So this agent network works as a CPU of your whole architecture that will do the layer selection mechanism, and also it will give you a proper result on how much computation should be spent on a particular sample. So moving ahead, in this case, our main network is basically it's exactly how we have any for any task. Let's say for classification, for regression, or any other machine learning task. For our experiments, we first constructed a stack of convolution layer networks, and we also use special fixed point iteration layers to specify like which layer it should be going to. And these fixed point layers, they enable increasingly the network to approximate complex functions as we go ahead, right? So another thing that I wanted to mention in this, even though we have like a main network, we have formed a composite function where, like, let's say G of the composite function G, which is the fixed point iteration function, where it takes each and every sample and then the neural network, it dynamically chooses the layer based on this unique characterization of each input sample. So that's a very important thing, because generally what happens in any straightforward network is like you will be just going from batch to batch, you will be learning that, and then you will be giving some output of some kind. But in this case, we are going sample by sample, and we are selecting adaptively, like checking at which layer it should be spending most time in. So the main part in this is basically the AgentNet as well. That is the CPU, as I mentioned, that is the CPU of this architecture. So it takes an input, it takes the input activations from the main network and makes a decision to select the most appropriate layer or a set of layers for each sample or in the batch. And as I mentioned, so this particular part will be basically the composite function. As I mentioned, so that is a G of X of I, which is the sample and the particular action that you have for that. And then it will be giving me the output of Y, which is where it should be going in that particular layer. So I just wanted to again specify how agent network works. So we wanted to guide the training of the agent network. So for any reinforcement learning problem, you have two main parts. You have the rewards and the penalty. So the reward function R is defined as some alpha of our accuracy that has been given, that has been calculated using through the training. And we subtracted with the penalty part, which is the number of consecutive layer counts, like how much time does it spend on that particular layer, and the control function, where it's like basically the layer selection, and as well as what was C in this case? So computational cost. Sorry, the computational cost. So this defines the penalty in this case. So again, so reward is basically the alpha into accuracy minus your beta into your computational cost into the consecutive layer count. And in this case, as I mentioned, so the output of the agent will be given to an adaptive softmax, because that adaptive softmax will actually check like how much temperature is there, and how much and at which layer do you actually have to go to. So how does the state of the agent actually works? So we just wanted to see if in the case of a state, it just says like, what do I predict in the state, or what actual output do I want if I had chosen some action instead? And that to take a trade-off of that state and the action part, we had to do a lot of experiments, and that's the reason. So for those parts also, we have a lot of algorithms, or we have a lot of like architectures in reinforcement learning itself, like for example PPO or DQ or DEQ networks, but we are not exactly taking those parts in that, but we are only considering the agent network in that. So that's why it's not exactly a reinforcement learning problem. Now, in this case, as I already mentioned, that the layer selection mechanism is based upon the dynamically selection by the agent net itself, and it also allows the network to adaptively adapt its compute complexity based on a specific computational need. And that's very interesting because in general, in any straightforward model, you do not know which sample requires more computation and which sample requires less computation, or which sample is basically easy or which sample is difficult. So that the model is not exactly aware of. So I wanted to share the model architecture of this as well that we have. So in this case, this is the main network. We have the inputs which will go in some stack. Let's say these are CNN network, CNN layers, and we will be calculating the activations of these layers and giving the input as activations to the agent. Now this agent will be it will be doing the computation, and then it will be giving us the output in the adaptive softmax. And then adaptive softmax will basically, it will select out of how many layers do we have, and at which point do we have to go and perform the fixed point operation. Now there are there are 4 cases in this case. So the one that you see here, the upper one, it says that the agent did not decide anything. It just says like however the input is going in that model, it should just go like that in the straightforward method, exactly how it happens in any standard architecture. But in the case of model 1, model 2, and model 3, what it says is like in the case of model 1, you should be having the fixed point operation on the first layer. In the case of model 2, it should be having fixed point operation in the second layer. And then similarly for model 3, it should be having fixed point operation in the third layer. Now, this is the amount of computation that you should be spending for that particular sample if the agent decides so. So this architecture it's still simpler, but the way that we have implemented it, it's kind of it has a lot of tricks that we will be discussing. So just to give you a more mathematical in a more mathematical sense, so we have layers, let's say from L1 to Ln, which is the main network, and some agent net, which is basically A, that has that has the input as the activation of the main network, which is the A1, A2, A3 to AN. And we get a probability out distribution from this, which is, let's say in this case, it's defined by P, where this distribution is basically followed by the softmax, the adaptive softmax. And then we calculate our reward function, which is the classification accuracy that we get from this training set, minus the penalty cost, which is the computational cost, how much time did the sample actually spent on that layer, and which layer did the sample actually select. So if, for example, if one sample or like multiple samples, if they're selecting just one layer again and again, or if they're stuck in that, then we know that there might be something wrong. That's the reason we need the reward function and the penalty function, value in this to be very precise in this case. In this case, the alpha and alpha beta are basically the hyperparameters that will guide your agent net to be more optimal. And the loss function of the entire architecture is calculated as the cross entropy loss minus some gamma with the reward. A gamma in this case is again some hyperparameter that we have chosen. So coming to the next part, where it gets more interesting, because now that we have already seen the architecture, we don't really know how exactly what's happening. So one thing which we can see from this case is like the backpropagation might be a little tricky, and yes, it was. So in any traditional backpropagation, in any traditional backpropagation method, you can prove that it's suboptimal for this DynaLay architecture because it has a dynamic nature and it also has the presence of fixed point layers. So for each sample, a unique set of layers is used by the agent net. And we also have to check, we will also be accumulating all the gradients, but we have to detach those, the fixed point at each iteration, because because we do not want to drag the computational graph into the next iteration. If we do, then it will the whole computational graph collapse. So that's the reason we had to modify a gradient accumulation technique. And for this, we used the gradient clipping method that worked very well. And that also proved that we can use it in the contraction mapping theorem that I mentioned before. The second part of this is the implementation of our implicit differentiation. So let's again consider the equation that we saw before, where we had some activation, let's say in this case, tan H. And we have a linear layer where the G is basically a function of your input and like X and input and input in this case, X and Z. So that function is given by this G of X of Z, where your Z minus tan H of that particular part. So if we differentiate this with respect to some fixed point iteration, then we can see that the same Jacobian term that is needed to find the root within some Newton's method as for computing the backward pass through your implicit differentiation, we can simply use this Jacobian and its inverse as well that we did in the forward pass. So we don't really have to, so this is the part. So in this case, you can see from equation 3, since the same Jacobian term is needed in finding some root within the Newton's method, we can reuse the Jacobian, and we can also, we do not have to store any gradients while we are computing the fixed point iteration. So that's something that was really interesting, and it also really helped in the case of fixed point iteration. And for those who know backpropagation and okay, that I'll come later. But in this case, the goal of backpropagation is to compute the gradient with respect to some scalar loss. But if you write this term out like how our gradient is in this equation 3, then it would look like this. So minus the loss of that with respect to the Z star, which is the fixed point, and the inverse of this of the composite function into your the composite function with respect to your sample. So even though we have applied this part, the implicit, even though we have this implicit differentiation formula in equation 4, in backpropagation, this term is computed from left to right, meaning instead of actually needing to compute the full Jacobian, which is partial differentiation of Z star divided by partial differentiation of X, we just need to compute the vector Jacobian product as shown here. So, and that, as a matter of fact, is very convenient because like how we have automatic differentiation frameworks in PyTorch, it's actually very easy to compute using that. And in this case, the terms in the terms of operations on the gradients, the transpose of the Jacobian are basically scalar valued function. So that's very convenient for us as well, and it works for the fixed point iteration. So again, however, I would like to emphasize that we don't really need to store and compute the actual inverse as we have in this equation 5. We just have to be able to solve the linear equation that is coming in this. It's basically like a linear equation that's arising in this formula. So I know this is kind of more mathematical, but we needed to spend some time on this because this is like a very important part in calculating the gradients and checking the gradient flow through our fixed point iteration. The third part is which we did for further optimizing is we use the orthogonal over parameterization. So this technique is just it's a technique where your weight matrix is in the neural network layer is factorized into a product of an orthogonal matrix. So that's the equation that we have in here, and it's very important because we also have it's important because we can stabilize the matrices that we have and also improve the gradient flow. Because before this, if we did not use it, we were seeing a very unstable gradients, or we were seeing the problem of overfitting and underfitting as well. So this was the methodology part of the whole of our network. Now let's move to a very exciting part which I'm very excited to say are the results. So in this case, we are comparing between two parts. First is a 3-layer CNN network, and second is the DEQ network, which I mentioned before, the deep equilibrium networks with solvers. As you can see in this table, we can see that the backward pass time for our case, in the case of Cypher 10 and Cypher 100, it's comparatively lower than what we are seeing in any 3-layer CNN network, as well as in DEQ solvers. Now, the problem with DEQ with solvers is that it takes so much time, and it's still not able to give us the actual result because of that. So in this case, we are seeing that the backward pass time, it took in seconds or milliseconds, but in the case of DEQ, it actually took 600 minutes. So that's like more than 10 hours. So that's not at all computationally efficient. So that was something that we were really curious about. Now, the second part, during our experimentation on checking the frequency at which your layer is selected, this is the plot that we wanted to present. So remarkably, the no layer or the straightforward option emerges as a more frequently selected. So what this means is that its ability to capture essential features across broad spectrum of tasks is going to be happen even if you select no layer. But then if you're doing any high computational power, high computational method, then that sample is being selected by the layer 3 as well. So what layer 3 means, like you're spending a lot of time, a lot of your computation in processing that sample and then going forward. So this was very interesting. Few of the results that we did here are with CNN and LSTM. So in this case, we used Cypher 10 and Cypher 100 as our base data set. And you can see from the results in this case is the convergence behavior of our models training and test loss is basically, it's really great, because you can see it's going to, the loss is below zero, and yeah, the loss for Cypher 10 and Cypher 10 training and testing is basically below 0. But for Cypher 100, since it's bigger than Cypher 10, it's definitely more than Cypher 10 in this case. So and also it also says that a model is basically scalable and it's also adaptable to different tasks and data distribution, which aligns very well to our core objective of this research work. Let's also show you the work for the LSTM. So as I mentioned before, that we wanted to make this a model agnostic architecture. So we used both our CNN and LSTM. And in this case, we employed fixed point iteration method on 2 datasets, which are the wiki text and the IMDb sentimental analysis dataset. And through this, you can see that for the test accuracy is almost achieving a really great accuracy. For IMDb, it's basically achieving around like 60%, but for wiki text, which is a much better data set for in this case, is achieving almost like it's hitting like 80%. So this was something that we wanted to show, and we wanted to also see and demonstrate that our architecture is equally effective for text-based task as well. And that also confirms the versatility across different data modalities and the task. One of the primary objective of this experiment is basically to show, this experiment is to basically show how rigorously, how efficient it is in each and every layer that we have selected. So let's say in this case, as I mentioned before, we have four options: model 0, 1, 2, and 3. So model 0 is basically a straightforward architecture that goes from input layer 1, layer 2, layer 3, and to output. Model 1 has the fixed point iteration in layer 1, model 2 again in layer 2, and model 3 in layer 3. Now you can see from this experiment that, so in this experiment, we can see that the incorporation of fixed point iteration into the increasing number of layer will yield a commensurate improvement in key performance metric, right? The test loss and the accuracy in this case, we can specifically see in the case of accuracy Like the straightforward model has more accuracy than just using a model 3 or fixed point on layer 3. It implies that not all the samples require that much computation, so they can just go forward. And again, the same thing goes for the for loss as well. We also did few experiments which mentions, we also did few experiments using the pre-training and the non-pre-training. The reason why we wanted to employ this pre-training part is because, let's say, like what happens if we warm up our weights or activations a bit and then try to employ this architecture. So we employed this for, we did a warm-up phase, which consisted of almost like 20 epochs for the pre-training and the main model, in the main model. And you can see from this results that the pre-training part is performing much better than the non-pre-trained part. And that actually implies that if the activations are or the weights are a bit learned before we start this architecture, start employing fixed point iteration, then this will give us a much better result than any other, than starting it from scratch. And that's what we wanted to show here as well. So again, for the case of agent, we wanted to be thorough with agent's performance as well. And as we saw, so this is for pre-training phase, we saw like the agent is performing really well in the case of rewards, and it's basically going up in a very not a linear way, but it's going in a preserved way that shows that it's performing well, and there's no breakage, or there's no part in this case where the agent is not trying to learn. So the reward, that's the reason, like the reward is kind of linear in this case. And you can also see how it's actually improving the performance metrics for this model in here. Another result that I wanted to share here is how agent's decision-making process is captured in this case. So in each curve on the plot, in this case, signifies the frequency with which the agent selects or elects to utilize a specific layer across the spectrum. So across the spectrum of available penalty. So in this case, as you can see, the layer 3 frequency, it will drop significantly before, significantly as you increase your penalty, which means that your agent is basically being more resource efficient. And as you can see with the purple or bluish curve that you have here, that is the 0 layer. So as you increase your penalty layer, it will be constant, but if it's a lot, it doesn't really matter, it will still go up. So that was something that we saw. And from the from the pinkish curve that you see here, that is the validation accuracy. So for each and every decision making that we saw, we can actually see like how the layers are being selected and what effect it has with the increased penalty cost of this. So that concludes my presentation on the architecture. So just to conclude, we presented a new architecture which is called the DynaLay, and that has the part of introspection as well as showing which layer is more important, and also being more computationally efficient, as well as showing the adaptive layer selection of a network. So the future direction for this case in this project, since this is, I don't want to state that this is I don't want to mention that this is like a state of the art work that we have done yet, because I feel like we have a lot of experiments that are still left in order to capture the whole part of this. So few of the things which I would like to do in this is basically using attention mechanism instead of the agent, or employing the attention mechanism for better weight selection. Also, we wanted to make this, we wanted to explore more intricate models, like for example, GANs or capsule networks, or something like generative AI that we have right now. And the aim of this architecture is to make it model agnostic. As I already showed you, that we can use convolution neural network and LSTM, but we wanted to also try it with transformers, or whatever other models, foundational models are present right now. So yeah, and the next part which I would want to do is like optimize this for a real world application, so that we can see how actually does it perform in any scenario where we have a real world data set and to see how well it performs. I'm sure it will perform well, but we still have to do a lot of experiments. So these are few papers which I have taken reference from, and that can be read as well. Really great papers. So I would deeply like to thank Dr. Sergey Pliss, who has been incredibly supportive and like amazing advisor, and really given me the given me the freedom to pursue the research direction that I wanted, even though he knew how distracted I get at times with different projects. So this has been really important to me for computing my thesis. I would also like to acknowledge everybody from Trends. I found only this picture since this was posted by you from LinkedIn. So yeah, really great people, and they have amazing ideas. They're doing really great work, and it's really great to see whatever like the work that they are doing is also comparable to the work that I'm doing. So it's something that we can talk about in common. And last but not the least, I would like to acknowledge my friends and family. Their constant support is something that I required at each step of my life, and this is also something that that has been really important for me. So yeah, this is and yeah, that's all. Okay. So I open the floor to the committee members now for any further questions and any discussions that you feel.
Yeah, I mean, maybe you can ask the questions if you can hear me from.
Sure, I can hear you. Honestly, it was a very great presentation. So honestly, I just had a lesson a day, so I didn't have a time to go through the project. So I cannot really provide a good scientific feedback. But you are working with Sergey, so he's the best, most suitable, and the best one who can advise you in this area for sure. And I have seen you hanging out with him a lot, so you probably don't need even my feedback. But I have one general question that I always ask. Can you explain to me what you are doing in the simple term?
What am I doing in a very simple term?
Yeah, what is the project that you are working on?
Absolutely. So we are trying to make an architecture that needs to be a self introspective in order to decide how it should be dealing with the samples, or in a much simpler way. We wanted to create an architecture. It's a first step of creating an AGI architecture. So in any in any implementation that you have seen right now, there are so many steps that you have to take. There are so many things that you have to take into consideration. But we wanted to remove that and let another agent, or in this case, the CPU, to decide what it needs to do for that particular implementation. So that's something that I will say in a very simple term.
So, and how it make a decision? Is it based on the sample? Is it sample-wise dynamic thing, or how the system make a decision?
So the system makes the decision, as I mentioned before. It uses the activations of each and every layer that we have.
But it is sample-wise.
It is sample-wise, yeah.
Okay.
So in this case, it will take each and every sample from, let's say, so this is like basically a main model that you have, and you have the activations A1, A2, A3, which will be the input to this agent network, and this agent network will be creating like a probability distribution that we will be having from adaptive softmax, and then it will be deciding what needs to be done ahead. So this decision is basically the main crux of this decision is being done by the activations from the network that you already have. Now, what happens in the straightforward network? Remove the whole part. You will be having the input, the activation will be going here, again, backpropagation, doing thing, but you don't really know if that particular sample is being properly computed in layer 1 or layer 2 or layer 3. It's just going straight forward. But what we are trying to do, we are trying to break that, and we are asking the agent to decide for that particular sample where it will be most computationally efficient, whether it will be just in layer 1, in layer 2, or just in layer 3. So layer 3 is basically something which is a very difficult problem for you, a very difficult sample for you, and it requires more time from the model to give you a better accuracy or give you a better output.
And can you distinguish between your work and like a reinforcement learnings? How is it different?
So reinforcement learning, basically, that's the reason why I wanted to specify this is not a reinforcement learning is because in the reinforcement learning, you have different algorithms. Like, for example, you have policy networks, you have gradient networks, you also have epsilon greedy network algorithms. In this, so those parts are those parts are something which can be done, but they are not required, or let me be more specific. In this case, we don't really care what the main model is. We don't really care. It can be anything, CNN, LSTM, transformers, and then it will be deciding on the fact of whatever activation that you have, on which layer you want to specify out. But in the case of reinforcement learning, it's a whole, like the agent in the network and the environment will be interacting with each other in such a way that they are just one whole architecture, one whole model. So there's no proper distinguishing between what exactly you want to do with that particular sample. So that's what I feel is the main distinction between this architecture and the reinforcement learning.
Okay. Thank you. And I'm guessing you are going to talk with Sergey to continue your PhD, right?
Yes.
Yeah, that's great. That's great. He's a wonderful advisor.
Yes,
Awesome.
definitely.
Yes.
Are there any other questions from?
No, that's good. And yeah, thank you.
So, I mean, I think thank you, Mrinal. This is great, and I'm glad I even took one picture, and we have the recording of that. But we maybe
Should I be?
I need to stop the recording. I forgot. My question is,